archive. So there we go. We got that going. And yeah, my goal today is I've started this yesterday. I'm looking for a SAT solver, and I went and I downloaded 6 different ones from the internet that are open source, and I did not succeed at building any one of them. I'm not going to try again. Most of them aren't going to build because they just have direct dependencies on Linux, and I'm not feeling up to porting them, especially not in this state where I don't even really understand their APIs or their internal functions, so I wouldn't feel comfortable trying to port something that I just understand nothing about its structure. A few of them I couldn't build because the build systems were so complicated, and I'm not going to try to build those either because even if I succeed at building them using their build systems, I would still have to figure out how to unravel that into a build script, and it's not something I'm up for. So instead, my goal here is going to be to just go through some of these, especially some of the simpler ones. I'll get started on the easy ones and just read the code and learn about their structure. So this is going to be just like a hanging out and reading session. If you're already watching, you'll get to sort of see the beginning of this process, and hopefully over the course of the next few hours, I'll start to build up a better understanding of how how algorithms for SAT solving work. If anyone has a question and wants to sit and chat, we're also just kind of hanging out and chatting. That today's a good day for that, since I'm not going to be like trying to be super productive writing code or anything. Just reading some code and maybe sharing some thoughts on what would make this code easier to read, or what I could do to actually get a SAT solver that works out of this experiment. So I can't remember exactly which one of these are the simplest one. I know this one is not simple, this one is not simple, and this one, I think this one is pretty simple. Yeah, this one's pretty close to simple. You can see I actually got some of it to build. I like completely trashed these folders when I was just like desperately trying to get them to build. I dropped object files all over the place. But yeah, this is like, if you just look at the C and H files here, let me like clean up the mess I made so that it looks cleaner like it's supposed to. There we go. So you can see that's not like a crazy amount of code, and that's all pure C. So maybe this would be a good one to read first. I also know some of these other ones, like the mini SAT is complicated. It's called mini, but it's like, we got the core over here, and it's all like separated out. It's in C++, which makes it feel complicated. It's not like a lot of code, but it's a lot of sort of like highly segmented C++. We got this one is a simpler one. Again, I made a mess. Let me clean up some of this while we're in here. So yeah, this one's a little bit simpler, but I don't know if I want to read this one first. I'm kind of drawn to reading this one first, and the reason for that is just that it's the one that I touched last, I think. And let's see, I think there's one other one of these that's pretty simple. This one, yeah, this one's a little more complicated. It's not that much more complicated, but there's like stuff in here. It might be useful to have this because it's got some like sample CNF files. I could get an idea of what that's doing. So maybe that would be a good one to start with. And if I remember correctly, this one was written as a simplification for this one, which is one of the complicated ones that I'm avoiding for now. And then this is a separate complicated one. So let's start with this one. I think this is the one that I feel like this is closest to just a single flat directory of files. That's pretty attractive as a place to get started. So I'm going to read that one and see what I can learn from why are we not CDCL SAT solver? Okay, so there's like, that's fine. How is the text here? Is this big enough that we'll be able to read if we're on stream? Or should I zoom in anymore? All right, looks like it's good. It's so crazy to me. It could be smaller. Nah, not for me. I like my text big. I like to have a lot of good screen space, but having too much text on the screen at once is like headache inducing. Uh, Makes me feel easily distracted. I like feeling like I'm really locked in on the key piece in front of me. So this is as small as I'm comfortable with. So if the chat says it could be smaller, then we're good to go. So yeah, so this is going to be a bit tricky because I can't build it or step through it. But I want to try to glean the main ideas off the code. So I'm going to start from main. That might not be the right place to start reading if you actually do the structure of the code and we're giving someone a tour. But as an explorer, that's the right place. Oh, and just for clarity, this right here, CDCL sat solver. If you look, that's the name of the repo on that's the name of the repo on GitHub. So if you wanted to look at this code yourself, it's open source GitHub code. Thanks to the person who put this out there for our education. All right, so let's see. Main takes an arguments file, argc, and so I'm just trying to like figure out. Okay, parse formula is probably important. So parse formula takes in file star, and yeah, you can see right here. Here's why I couldn't build this one is because it uses getline, which is this Linux system thing. I should check because I might have like also fussed with the code a little bit. Yeah, let's restore that file. It looks like I changed main slightly trying to get it to build last night. So let's put it back to the way it was. I don't know what I changed. Sorry if I bumped the mic. The indentation is one space for me. If you don't like that, you can see that the code is actually not written that way. I just have my virtual white space layout system, which will take the white space and do this. I don't need very deep indentation to get the idea of blocks. And while I do, like I just made an argument about, I don't care that much about having lots of stuff on screen. Horizontally, that's not as true. I sometimes have a longer line. I sometimes have deep nesting. And so horizontally, I like to scrunch stuff up. I don't need very deep indentation to get the idea. If it's hard to read, I can like modify it to like at least 2 for the purposes of streaming. But yeah, again, just my weird quirks of how I like to view things. So let's see. Parse formula, like I said, looks like it's pretty important. And if we go into it, we can see right in the heart of the... Oh, I guess I just need to do it again. Right in the heart of the parse formula function is this getLine function, which is dependent on... I need to be able to be on Linux to... This is a not C standard or something, because I can't build because of this function here. But this is probably doing something pretty important. At least it's probably, it looks like maybe it's taking in a buffer as a file stream here, and then line buffer is there. Line, oh yeah, s size t was the other thing that didn't compile before. I don't know what s size t means. But the line comes out here, and then we do something with it. So it's parsed by line, and then it's doing something with formula clauses. So F starts with, probably it's building like a data structure for a formula out of the incoming text. And yeah, because you can see here it's scanning. Oh, s size t is assigned size t. That makes perfect sense. Okay, yeah, they probably have like a read size can be negative for an error case or something in that case. So scanf grabs the line, and this is a function that I never feel comfortable using, but it's basically reversing a printing operation. So it's grabbing stuff out of this line and putting it here. So we get like a character for the directive. We get weirdly, we already... Oh, it's redo... Yeah, okay. Character for the directive, a format... Oh, it's parsing the line several times. So once to figure out the directive itself, once to figure out num variables, num clauses. Num variables, less than num clauses, less than equals 0. Continue, formula, create, num variables, num clauses. So it's initializing. Why don't we... Okay, I think that reading the parsing might not be the most useful thing. Probably the most useful thing is going to be to look at those formula APIs that are letting it that are constructing the data structure. I think we'll figure out the general gist of the data structure from these functions. So let's put a flag in the ground for that. Where? Right. Okay. So formula C, we want to read this section because this looks like it's setting up the data structure of the formula. And then the parser is just populating and constructing a data structure of that type. And then if it gets a formula, then this is the second flag in the ground, which is where the solve happens. So this will give us... This will give us the solver. Oh, awesome. So I just got someone in chat, JVS Tech, who is telling me that there's a SAT solver that does build on Windows, which is great. I spent last night looking around online, Googling C library Windows, C/C++ library, SAT solver, all these different things, trying to find something that would work. And after 6 separate things that I tried, I just kind of gave up and I was like, all right, I can't find one. Maybe I'll read about this and learn about it. But if you're recommending one, I'll put that on my list. Let's start a list of things to do. This is good. So we've got right now I'm reading CDCL. This one looks really simple. And I want to look at the formula stuff, and I want to look at the CDCL solver stuff. And then next, what I'm going to do is I'm going to go and check this one out. So Z3, SAT solver in C++ that builds on Windows. We can check that out. It might still be that I end up needing to make tweaks or something. I'd really love to get the feeling of a single header C library feel that I can just easily drop into almost anything anywhere with no build complexity and no operating system dependencies. And so if Z3 gets me closer to that, that would be great. If it's close enough, I might just stop there, or I might continue this project. I'm kind of feeling like maybe I want to make that, but I don't necessarily want to rush into it if I don't appreciate how SAT solvers get built. So I want to take some time to learn the structure either way. But yeah, we'll take a look at this and see how close that gets me to what I want. It might be 80% of the way there, in which case I might just stop and say, all right, let's just play with this library for now, and the pressure to the interest in learning more might fizzle out. But we'll get to that next. Okay. So then there's the solver, and it looks like that's kind of most of what's interesting about this. Num variables. Okay, so from what I'm gleaning off of this, the solver is going to take in a formula and it's going to return a model. If that model is a null pointer, then there was no way to satisfy the formula. Oh, there might be people watching who don't know what SAT means. So I was going to kind of try to not spend a lot of time filling in stuff I don't know, but I do know at least what SAT is. So for anyone who's watching who's like, what are we talking about? What's a SAT solver? SAT is the problem where... SAT is the problem where we have a Boolean formula, we have a bunch of Boolean variables, right? Right? We might call them x1, x2, x3, etc., right? And then we have some formula, and that formula is okay, we want x1 or x2 and not, let's say not will look like this maybe, or I want something easy to type. Yeah, not x3 or x2. And it's like, okay, so here's my formula. I want to know, is it even possible to make this whole thing true? And if it is, how do I set all the variables to get there? And then there's a bunch of finer grained things you can do with it. So like you can say, okay, if I fix certain variables, how does the formula simplify? And can I still solve it that way? As you can, there are ways to like modify it and use it more incrementally than that. But like the whole chunky idea is just, we're talking about Boolean variables, formulas of ands and ors and logic on those. And you can add more advanced stuff like equality of variables or implication signs that are just, they're just more like syntax sugar almost on top of these basic ideas. And so you can make it a thing where it's like, okay, can I do this? Like, can I solve this? And then it turns out that there are fun things that you can build with a tool like that. It's like a little bit of a magic spell, but it's also a hard problem. Like the computationally, it is non-trivial to solve this problem. You can just like, there is a trivial solution, but it's not very efficient, which is to try every assignment until one of them works. And so SAT solvers are attempting to find a fast way to do something that is inherently impossible to do fast in the general case, but you can, for practical purposes, get pretty good stuff, is what I've heard, and that's what we're learning about today. It's like, what do we do practically to make these things work better than what you would get from just trying every combination? So yeah, and there was also folks talking in the chat now like, what's the applications of this? The application I've seen is, yes, there's like logical stuff in compilers that they can be used for. They are also super useful in things like if you're doing a crypto hash or a cryptography thing, and you're like, hey, I assert that there's no way to create, to create a hash collision here. If you go and read some of the research people did on Meow Hash, they use a SAT solver to show that there's a vulnerability in Meow Hash, which didn't defeat Meow Hash's purpose, but did like knock it down a few grades of how strong it is for security purposes. And basically what they did is they modeled the way that the bit shuffles worked for creating the hash to show that there are regularities in the pattern that would allow you to create like uh, an engineered input to generate hash collisions if you are generating malicious input. So it can be used for like that kind of like searching a large space of possible ways to cause something to happen. It's also like the classic example that people use is like Sudoku. It can be used for solving logic puzzles and stuff. Yeah, Casey knows about it. Casey definitely knows about it. Like I said, it wasn't a defeater of Meow Hash. It was more like when they developed Meow Hash, they thought it was at a certain level of security, and then it was never intended to be a security thing, but the person who was sort of helping Casey develop it believed it was at a certain degree of security, and then this other person, or maybe the same person, like ran this analysis on it and found like, no, actually you can manipulate the bits in a certain way in your input so that this is still good for what Casey wanted, which was like content hashing of non-malicious input, like game engine kinds of stuff, where you're not expecting to get random input from users that could be attempting to exploit the problems of the hash, but that it was not as secure as they thought, and so it didn't defeat the purpose of Meow Hash, but it did like knock it down a security grade. But yeah, they're all fully aware. It's a cool paper too. Maybe I should go find that and link it for y'all. Meow Hash, cryptanalysis of Meow Hash. It's cool because the paper I'm talking about, like the article I'm talking about, has like an interactive HTML element where you can, yeah, this is it. It has this interactive element where you can like play with the bits on the input and try to get it. I don't know if this is the interactive version, but it looks like that thing I just passed by. Where is the interactive version? Yeah, but you can see that they talk about how they use a SAT solver to accomplish this. Anyway, let's go read about the formula. So I want to see more about formula. Nice, simple. Okay, so that's a little annoying. So stylistically, something I have to watch out for, a little trick they're pulling here is they're hiding their pointer inside their type def. So they're making a struct formula and defining it, and then when they define what the formula type is actually going to be, they make it a pointer to one of these. So whenever we're looking at main here, this looks like they're returning a struct called formula. What they're actually returning is a pointer to a struct called formula because they've type defed formula with this star here. I think that's some C nonsense. I would never recommend doing that. I find it very confusing when something is actually a pointer, but it looks like, but it's not written explicitly in the places where it gets used. Also, the fact that it's like there's no way to directly talk about the formula struct except through its pointer, that's a little weird. But anyway, nitpicking. Let's look at this data structure. Int array, int array. So I know what an integer array is. I'm just curious how they're structuring it. Buffer count, buffer size. Okay, so we got like a growable array of we've got like a global array of integers here. Int array, append. Yeah, okay. I get the idea. So each of these is a pointer to one of these things. Again, hidden pointer here. So it's a pointer to a buffer and a count and a buffer size. And this is as well. And this tells us how many variables and clauses. Clauses. I wonder, this might not be a general stat solver. This might be like only capable of dealing with the CNF like after it's been processed. So okay. So CNF stands for conjunctive normal form, and that's a little bit restricted. In conjunctive normal form, you can only do ands of or, so you get like something that looks like this, like x1 or x2 or not x3, and so on. So a 3 CNF would be one where you only have up to 3 variables in each clause. And so when they say clauses, it makes me think that we're talking about conjunctive normal form because we start calling each of these a separate clause. Right? And it turns out you can translate any formula into this form of like ands in ors inside of ands with no other structure. So if they're talking about clauses, like when it can be arbitrarily nested, right? Because you can imagine you could go like that becomes x1 and x2, right? Or something like that. Right, you can have this like nesting where it gets complicated, whereas in this form, you don't have arbitrary nesting. You have a strict set of clauses, and there's a way to translate from this form to this form that it has equivalent properties. That is, the variables will have the same assignments when we make the whole formula true. But we also have to like add in extra variables to make this work and stuff. So this requires a sort of interesting translation. And since they're talking about clauses here, it makes me wonder if this is already in like a conjunctive normal form. So let's take a look at what this add clause stuff is gonna do. If we look at add clause, probably gonna guess here, clause is probably a pointer to a struct clause, and okay, so a clause comes with some literals possibly, and then some literals count, clause bounds. So let's go look at that in a minute. Clause bounds. I don't know what to make of that yet, but it's just an array of integers. Okay. Something there I don't quite get yet. Somehow we're specifying the clauses in this data structure, but I'm not sure how. clause bounds count. So count clauses, clause bounds count. I suspect I know what it's doing. I suspect I know what it's doing. Literals count. Yeah, okay. Okay, so here's what's happening. You see here, we're pushing onto this, or we're appending onto the back of an array, another array of literals. So if we go and look at what the clause is, we're going to see, here we have an array of integers. Guess they have a const version of that, so this array probably doesn't need the ability to be appended to. It's just a bank of integers in a buffer. Is that the idea? The non-mutable version. So yeah. All right, okay. So that's good and all. We have the clause comes in, we have the literals, so we're pushing all of those on. We might be pushing like 5, for instance. So if I push 5 onto those 5 literals go onto this array here, and then we've grown the thing by 5. We take the length of the array at that point in time and put it on the clause bounds. So what we're ending up with in this data structure, I'm going to just start typing some notes right into the code here. So how this data structure appears to work. We have the literals is like an array of integers, right? And these could be any arbitrary things, right? We don't have any particular idea of them being like what their structure means yet. It's just an array of literals. And then we have this clause bounds thing. And the clause bounds has some restrictions. So it might say like 3, and then let's see, 3, 4, 5, 6, 7, right? And so what this is talking about is this is equivalent to saying that the clause bounds are actually sort of offsets into this thing, like 3, 5. Oh, I counted wrong. It's 0. It's 0 based. So we want 3, 4, 6, right? 0, 1, 2, 3, 4, 5, 6. So we have these like pointers into this one, and so each of these, like clause 0 is everything from 0 to 2. Clause 1 is everything from after 2, so 3 to 4, right? We can go here, we go, well, look at this. That means we're looking at the clause that begins at 3 and ends at 4. Or it could be that these are actually, they're probably actually structured like this, right? So 3 means that our first clause, clause number 1, spans 0, 1, and 2 and stops there. And then our second clause, yeah, this is a good picture for it. This explains the idea. So each of our clauses looks like this, and is the way it is described with data that looks like this. Okay, so clause is just arranged inside this. And what I'm really saying is that the clause bounds looks like this, corresponding to the clauses, which are not literally represented in the data structure, but we're trying to capture this concept. And we're capturing it with this literal data. Like this is the actual data that captures that. Okay. So we can add clauses, count clauses. We can get a clause, and that's probably going to do the thing where it looks up into here and then grabs the range. So let's take a look at that just to confirm the hypothesis. We formed a theory, and now we're going to look at new code that has the opportunity to confirm or disconfirm this theory. Clause index equals. So yep, they have a special case for 0 where the lower bound becomes 0, and otherwise the lower bound is that index minus 1. And then the end is the index given there. So we have a start and an end, and this is an exclusive. This is half inclusive, half exclusive. And then we form one of these constant arrays by pointing it into that section of the array and return it. Hey, Bitwitch. All right, so we know what a formula does, and that gives me more reason to think that this is going to be solving conjunctive normal form, because we don't see anything in here about clauses referencing other clauses. And if that's the case, it would be hard to have arbitrary nesting structure, right? We would need some way to say that this clause here is made up of this expression and this expression, which we don't have. We have a way of forming this kind of data because we can say, like, okay, list out the literals, list them out again in a different way, and then mark the ranges. And it's just understood that the logical relationship between the ands and the ors is a certain way. So that's good to know. We're not going to learn from this how to convert flexible formulas into conjunctive normal form, probably. But we will learn how to take conjunctive normal form and solve from there. So we want to look at what the solve looks like. So this is the heart of this whole project, right? This code we're reading, this is the heart of it. It takes in that formula data structure we were just investigating, and it produces a model. So before we go and read the code and see how it produces a model, maybe we do want to know what a model looks like. Just to get ourselves familiar with the data structure on either side of this computation. Okay, so value false is -1, value true is 1. Value unassigned. Okay, so a model value can actually be true, false, or unassigned, which is cool. Makes me wonder. Okay, yeah, so when we go to print this out, if we could run the code, it would completely change how we would interact with learning it. But maybe when we go and check out Z3, we'll see something a little bit more alive than this experience. But you can see here that yes, indeed, it is prepared, even when the whole thing is done, to see unassigned values. So it could be that if it's possible to satisfy the model, that it's possible to do so, and certain variables can go either way, and it makes no difference. So, for instance, if we look at my scratch over here, if we made x1 true and x2 false, then this would be true because x1 is true. This would be true because x1 is true and x2 is false. And so then this whole thing here would be true because even though this hasn't been determined yet, this would be true anyway, and so x3 could be a free variable. All right, so let's go read a little bit about the model data structure. So the model has an array. Interestingly, the assignment does not hide a pointer. They didn't use the assignment type to hide a pointer. So that's, again, a reason why when I'm in C, I would never do this. If you were literally always doing it, I could maybe see that you have developed a style of thinking of things this way. But now, if I haven't gone and read the definition code, I might make the wrong assumption from time to time about whether assignment is a pointer or a struct. So I think it's an easy source of confusion to avoid. But anyway, so number of variables, number of assignments, number assigned. Okay, so the number of variables is just a property of the formula. It's not a property of the solution to the formula. Whereas the number of assigned might be something that gets changed over time in a solver. Starts off at 0. When we assign, yeah. I see. Okay, so this is interesting. So we have this idea of assigning a variable inside the model. So we can say, okay, variable number n, right, give it an index. Here's the value I want to give it. And we can give it either true, false, or unassigned, which means it's free to vary. And then, I don't know what these do yet, but like you can see here, it's doing check to see if we're actually doing anything that modifies the value. So if the value is not modified, no change happens. But if the value does get modified, we grab an index, or we use the index to look at an assignment. So it looks like maybe the array of assignments here is based on the number of variables. Yeah. When we create a model, we set the number of variables, and that tells us how many assignment structs are in this array here. Okay. So we have these assignment things, and we still need to figure out what, like, we know what the value part is. We don't know anything about this, but then it comes in here and it says, okay, the value has been changed. So now these things which we don't understand yet have been updated, and then we keep track of how many variables are assigned by looking at what changes occurred. So if the old value was unassigned and we know we're changing it, then we've increased the number of assignments. And otherwise, if the new value is unassigned, then we must be changing from assigned to unassigned, so we decrease. So we can keep track of how many variables are assigned that way. So this is a number between 0 and the number of variables, which tells us how many in this whole, it's like a counter of how many of these have been set to true or false. Evaluate, what I would expect this to do is to figure out if the model is true or false based on the current assignment of the model. But it also takes a clause. Oh, so the model doesn't actually, interestingly, this is like evaluate a clause. So this does not actually evaluate an entire formula because the model isn't like a pointer to a formula. The model is just a bunch of variables that we can twiddle their states on, off, or intermediate, like unassigned, right? So each variable has one of three states: assigned, true, false, or unassigned. But the model doesn't know anything about the relationships between the variables. That all lives inside the clauses and the formulas. So to evaluate, we're passing in a model, which is the assignment of the variables, and the clause, which is the relationships between variables. And then what is this part? Unit literal index. Unassigned count equals 1. Unassigned count. Okay, so what this looks like it's doing is this is, in the process of evaluating, it wants to do an extra step of work. It's doing one extra piece here, which is it might, if this is not null, then it'll also do this logic of if there is one unassigned variable, then we will return the index, the variable index, right? It's the it's not the it's not the identifier of the variable, but the index into the clause where that variable is found. Does that make sense? So like we have a clause, and that clause can be like 55, 13, 100, and then if we have 55 in our model, right? In our model, we say like, okay, 55 is true, 13 is unassigned, and 100 is false. Then what this will do is it'll say, hey, if one of these is unassigned, then I want to know which one, and I don't want to know the number 13. I want to know the number of the index. So it's like this is, 0, 1, and 2. So it's indexed into the clause where the lone unassigned variable exists. If there are more than one, then we get back -1 to indicate, hey, there's not just one of these. Interestingly, unit literal index. Interestingly, and something I would do a little. Oh, here it is. I was about to say something false. Here it is. So at the beginning, if we start, it also sets to -1. So that can also indicate that there are no if all of them are assigned, or if 2 of them or more are unassigned. It's only if there's exactly one unassigned that that'll return us something. Okay. This is another insert by me. Okay. Later, Brett. Have a good time on Wilmot's Warehouse. Alrighty. So evaluate should be trying to figure out unassigned count. So if we have a bunch of ors, weirdly it's only returning either false or, oh, no, okay. Right. Returns in the middle of the function. Gotta watch out for that. Okay, so if it finds any of them are true, then it returns true. And so this is only reachable if we are in the negation of that context. This is something that I know I disagree with a lot of other programmers, but returning in the middle creates such weird conditions for your code. So this code here, what it literally is saying is if no variable is true, but it doesn't say that because it's implicit in the fact that we didn't return yet, which makes it a little harder to figure out what it means at a glance. If no variable is true, then if any variable is unassigned, return unassigned, otherwise return false. Okay, so the whole logic of this, if we split it up, one piece of the logic is this, like, hey, is there exactly one unassigned variable? And the other piece of logic in this evaluate function is take the highest truthiness that exists. So if there's at least one true, the whole thing is true. If there's otherwise, if there's at least one unassigned, the whole thing is unassigned. Otherwise, if the whole thing is false, then the thing evaluates to false. So this means a clause is like a bunch of variables ordered together, right? Something like x1 or x2 or not x3 or not x4, right? So this is what a clause can be like, and it's just always ors. It's just a list of ors. It's just a list of variables ordered together, I should say. And the variables can all have that not on them, which we haven't actually gotten to the part where we can see that that's true. But it should be. All right. Backtrack. What does backtrack do? Decision level. Okay, so what this is doing is it's giving us a way to unroll some assignments. So we have this model thing. We can add assignments into it. So we can say, like, you're true, you're false, you're true, you're false. And then we might want to say, all right, let's go back to a state before all those things got assigned. And so when we're assigning them, we still don't know what antecedent index means, but the decision level makes sense. Probably as we assign things, we expect the decision level to be an increasing integer. However the user wants to increase it is up to them. And as they increase it, they're creating buckets. Kind of like in an arena where you say, like, okay, increment my decision level, and now all the decisions I make at this level are bucketed together. And then I can unroll to a certain point by going back a certain number of decision levels and saying backtrack to that decision level. And so everything that was made at that decision level and everything made after that decision level will be unrolled. If the value, but hold on. If the value is already unassigned, we don't touch it. Okay, these continues are again, same thing as returning early. The logic of everything that happens after a continue is actually like implicit negation of what came of the condition that came before it. So what this is saying is, if the value is not, I'm just going to modify this so that I can read it. If the value is not unassigned, then if the decision level is less than or equal to the decision level we're rolling, so if the decision level of the assignment is less than or equal to the decision level we're rolling back to, then we increase the number of assigned. So we increase the number of assigned. Why do we do that? Oh, I see. I see what's happening. Right. So we're actually, we're zeroing out the assign counter, and then with each so if I understand correctly, we're looking here and we're going, okay, these are the ones we keep, and these are the ones we undo. Right? So when we undo it, we just set it to unassigned. If we keep it, we count it, because we're starting from 0 and counting all of them again. And then model free, that's boring. Okay. So we know what the model can do. We can assign variables in it. We can evaluate a clause. We can backtrack. Now we want to go and look at that solve. Yeah. Okay, so here we're getting long lines. I'm going to go into single panel mode so we can see this big boy file in super wide mode. Okay. And I'm also going to turn on the highlight line at cursor because it looks like we still have line wrapping here and there that I want to be able to see. All right, so right here, stylistic note that I don't like, we're doing function pointers, which fine with function pointers, but specifying them out in this like long form here is not ideal. It's a little hard to read. I like to type def them first without a pointer, so it'd be like variable picker, let's call this like a pick variable function, and then it would have like this, so that would all stay the same, but then when we want to make a function of this type, we go pick variable, let's see, what's the name of this? Here's this right here, buried in the middle, that's the name of our variable. And we go pick variable function pointer, like that. So now we have a function pointer with the same type as before, and we can see that it's a function pointer because we see the pointer here when we create the variable. And it's very easy now to read the signature of the function because that's been split out. So stylistic note, if you're doing function pointers in C, it might be a little bit more verbose, feel clunky to type it if you're already comfortable with this syntax, but I think it makes such a big difference to how easy it is to comprehend the code. Analyze conflict function, and of course you can like then move these into headers along with everything else. You don't have to put them here like I'm doing here, and then you got this reusable function signature pointer type thingy ready to go. So we want this here, and we want to preserve that variable name, and we want the analyze conflict function pointer like that. And that, yeah, you don't need to put the ampersand when you're assigning function pointers. The name of a function is a function pointer. Actually, the address of a function pointer is the same type. Like, this is a whole weird bit of C nonsense. I can't build anyway to make sure that I didn't screw that up, but that's just a rough translation into a style that I'll actually be able to read when I come back to, like, when I bounce back and forth to actually understanding what this does. This is going to help me a bit. Okay. Okay, how does the solve function work? You know, also I'm going to just pop over here and pop that right there. So they wanted to hide it because it's not like an exported function, but I don't really like the feeling of that. I like the way, I know people don't like headers, but I like, one thing I like about having a header is that it creates this like summary of the file that you're looking at. And so I like all of the stuff that helps complete the summary to be in the header, even if I'm not exporting it. Like I don't use it the way people do, so it's not really a stylistic thing so much as like a strong preference on my case to just put the declarations in the header, so that now I can look at the header and we could actually continue this concept by going like, yeah, there you go, there's the header that this actually would go with. All right. So solve. We create a model with the right number of variables for the formula. All right, we're gonna need to know what unit propagate does first, it looks like. F is our formula, M is our model. Let's go read about unit formula, or unit propagate. So we have a formula, we have a model, we have a decision level. Returns -1 when no conflict. Returns conflicted clause index otherwise. Okay, so this is going to tell us what it says unit propagate. I think what it means is like locate conflict clause or something. Analyze unit propagate. Okay, I'm already forgetting the name of this thing. Unit propagate is going to live down here. This little helper thing. All right, so the unit propagate takes a formula, takes a model, takes a decision level, and let's see. It's going to start with the unit literal index at -1. Unit literal index. So yeah, it's popping those out from the evaluates. We saw earlier how that works. If it comes back and it's not -1, so there's gonna be some logic there I need to read through more slowly, but it's not, so it's only, okay, here are the returns. This is what okay. So it's just, I know that I'm fighting an uphill battle, but returning in the middle of a function is just so confusing. I don't know how people think that makes code more readable. It's so confusing to me. Okay. So here is where the other return occurs. And it's just returning. Okay, so if something evals, okay, now it's starting to make sense. We're looking at agent clause of the formula. If one of them evaluates to hard false, remember what that means. That means the whole clause is false. So again, we're looking at a thing like this, and it can go on and on like this, right? Having all these things anded together. And so if any one of these is fully false, then the whole thing is false, because it's a big chain of ands. So if any one clause comes out false, the whole formula comes out false. And so what we're doing here is we're looking and seeing, have we gotten to a point where one of the clauses is a full false? And the way we're checking that is we're running the evaluate function, and the evaluate function returns a full false if every variable in the clause is assigned false, right? So we're using this model. We're going check the clause. Is it fully false? If it's fully false, then that clause is a conflict. And what we mean by conflict is that this particular assignment of variables doesn't work because this particular clause has become fully false with this assignment. So we return that index. Otherwise, if we keep going, then we're continuing the loop. We check and see if we got an unassigned. And if it's unassigned, then if it's unassigned, we look at the unit literal index from here. So here, if there was a unique unassigned thing. So for this to be, let's back up. For the whole clause to come out unassigned, what has to be true? Well, if anything in there is true, the whole thing comes out true. Like, all we need is one true variable. So one true variable means we're done, we're out, this clause is true. That means there's no trues, and since there's only one unassigned, everything in there must be false except for one thing. One thing must be unassigned. And that one unassigned thing has come back to us in this integer as something other than -1. And so whatever that thing is, if that thing was false, the whole thing would become false, and we would lose the game, right? We would not be able to find an assignment. So that one spot we now can deduce must be true for the whole thing to ever work out, and so we're sort of forced into assigning true onto that particular variable. So what we do then is we take that index, we look at our literal buffer, and we go, okay, inside this clause, this index must come out, or this index tells us what literal variable we're talking about. So we grab that literal, and we stick a true. Oh, okay. So we just learned something that I haven't found yet. Literal here, do you see this? If literal is less than 0, value equals negative value. What is that doing? So remember, true and false were 1 and -1, right? So what we're doing is somewhere along the way we had to encode the concept of not. So a clause can be a list of variables, but those variables can either be their positive self or their negative self, right? So like here I have the positive x2, and here I have the negated x2. And we want to be able to, like if we were doing an abstract syntax tree, we would introduce a separate node for a negation, but we don't want that in this case. Instead, what we want is whenever we refer to a variable, that's either its positive version or its negative version. And the way they are representing that is with a signed integer, so that the variable 5, or the literal number 5, can either be 5 or -5. And if it's -5, we're saying that we're talking about the negated version of 5. It's clever, right? But the way we actually are implementing that is we're going, okay, so we're not saying make this variable true. We're saying if the variable is its positive version, make it true. But if the variable is its negative version, make it false. But you can see then we take the absolute value of the literal. You see that? So if I set the variable to true, I'm setting 5, like if we're talking about 5 and -5, if I get -5, then I actually go and I set +5, the variable, to the value false. Is that making sense? Right? I'm either way, I'm setting the variable number 5, but I'm either going to set it to true or false based on whether or not it will have that negation in the clause. So what that makes me curious about, so let's go back to model. I might have missed something here. Here it is. I skipped it. I skipped over it. I skipped over it the first time through. Yep, you can see right here the absolute value thing happening. Okay, I completely missed that on the model part, but there it is. Now they line up. Makes sense. The negative version of a variable means the negated Okay. Yep. Missed this on the first pass, but this makes sense now. Okay. I feel like I've gone over the hump on this code. I've gotten to like the 80, 90% comprehension. I know what this code is doing now. Are there any files in here I skipped? Most common variable picker and UIP conflict analyzer. These two might be interesting things that I don't know anything about yet. But we know what unit propagate is doing. Let's go back up. So I think I still need to learn what solve does. I need to learn how those fit in. But I'm at this like 70 to 80% understanding point now. I have a model. I know how we're evaluating it. I know how this propagate thing isn't just locating. It's serving two purposes. It is locating the source of a conflict, but also propagate is correct in the sense that when it finds variables whose state are forced, it is applying that force, right? And by force, I mean that a particular clause has gotten to the point where a single variable is left in that clause that is unassigned, and all the rest are false. And so that unassigned variable is now forced into this true state. Otherwise, the whole thing will come out false, right? So these are single isolated variables that have to be true. Their value, or not that they have to be true. Their value is forced, either true or false, so that the clause therein comes out true. Okay. So that's what the propagate function is doing. That was the first line of the solve. So the first thing it does is it propagates. It starts with an empty model. So I guess what that first propagate is doing is if there are any clauses with just a single variable, it will find them and deal with them first. So like if you wanted to use these conjunctive normal forms to say like, okay, I want to add in an assignment. Like I've set up my formula and I'm curious what happens if x1 has to be false. Well, then you just put in that, right? Now x1 has to be false. You've as the user used the formula system to fix the x1 variable to false. Okay. What happens next? Now we got to figure out what decision levels are going to be about and stuff like that. So we're trying to get all of the variables assigned. Here we're calling that pick variable. We don't actually have to do this. C is confusing, but you can call a function pointer as if it's just a function. Maybe this is obfuscating rather than clarifying syntax that I prefer, but it's easier to read. It's easier to read for me. It loses the information that this is a function pointer, but it gains the like nice, straightforward clarity of function name, function parameters. M variable value. So, yeah, we're gonna need to know what that does, but it looks like it's returning out. These right here are outs. Yeah. Pick variable. Okay, so we need to learn a little bit about most common variable picker. model value, boom, boom, boom. So I think this, it must, yeah, this must be where some of the heuristics are happening to make things go faster. So here, we could oversimplify this to just imagining that the variable picker's job is to give us the next thing to assign to see what happens. And the way that works is we go, is this going to be a recursive function? No, okay. Let's see then. So we increment our decision level, we assign whatever this gave. So this gave us a hint of something to try. So when we propagate, everything that happens when we propagate is forced. If it's still not determined that this is impossible because we have a conflict clause, we make progress by picking a variable and a value and saying, let's see what happens when we fix the state of this variable. So then it assigns that variable inside the model, and it tells it the decision level of that assignment from right here. The conflict clause index, we then start propagating. So the propagation should then find all the variables that need to be forced into a particular state from that decision and see if any of the forced outcomes lead to just a fully conflict clause that cannot make progress. If there's no conflict, so the rest of this is if there's no conflict. Right? Conflict clause index. Oh, this is if there is a conflict. If there is a conflict. So it does not equal -1. -1, if it did equal -1, that would be no conflict. We picked a variable assignment that just works. If there is a conflict, then this will be something other than -1. A little hard to read the meaning, the abstract, the sort of conceptual meaning of index tricks like that, but that's what it means. Okay. Learned clause size. So here, we're analyzing the conflict. We don't know what analyze conflict means yet, but let's get an idea of what the inputs and outputs of analyze conflict are. So the note Allen, the pick variable function has as its input a formula and a model, and as an output it has a variable index and a Boolean assignment or value, right? Yeah, a Boolean. We have a variable index and a Boolean. So in comes the formula and the model, out comes variable index Boolean. That's what our pick variable function's basic structure is. And we don't know the internal guts yet, but it's intuitively somehow it's coming up with a good place to place a guess on how to make forward progress. Now, what is the conflict? What is analyze conflict functions structure? That's what we need to figure out next. So analyze conflict. It looks like it's taking in a formula and a model, and it's taking in the decision level and the conflict clause index. I suspect I might not want to. I'm not sure what the decision level, I'm not sure what role it's going to play here. So I want to go and look at that. And what's coming back is a beta and a learned clause size. and a learned clause literals. I don't know what any of these things mean. So these are the three things I need to figure out what that's about. If they come back in a bad state, then the whole thing is unsatisfiable. Otherwise, we know from here there was a conflict. Here we analyze the conflict, and it might be that this conflict, for whatever reason, is just not something we can come back from. But if we can come back from it, then we backtrack to the beta level. Okay, so the beta is the backtrack level we want to go to. And the learned clause, buffer, learned clause literals, learned clause size. Oh, so we're learning. Okay, we're forming a new clause, which is something we've learned, a relationship. Interesting. So it's learning. So, okay, what I'm getting from this, I don't know how it works yet, but the structure I'm seeing is that we've put in a formula to begin with that's made up of these clauses. And when it runs into a conflict, it analyzes the conflict and figures out how did this happen. And it then either says there's no way to get around it, we can't finish this formula, it's unsatisfiable, or it learns something, and it learns something in the form of a new clause that it can add to the formula. Presumably, the new clause is structured in such a way that it helps to force things down better paths in future iterations of the algorithm. So it's learning structure that is deeper than what is on the surface and adding it to the formula explicitly over time. That's my guess. I haven't actually gone and seen how this is working at those levels, but that's my guess of what we're looking at. Okay. Interesting. We add that clause to the formula. This memory management, so it'll be interesting. If I rewrite something like this, it'll be interesting to see how the memory management turns out for me compared to how it has to turn out with malloc and free. I wonder if it'll be better or if it'll be more difficult. Learned clause literals. It looks like this must have to be allocating new memory for the literal clause that it returns, for the clause data that it returns. Okay, so now I actually do know what this is about, though. It's returning. It comes in with a current decision level. So let's add that here. It makes sense now. And it comes back with a decision level. This is the decision level where it recommends backtracking to that decision level. It comes back with new clause data, right? And that clause data then has to be inserted into the formula after, and the model has to be backtracked to this decision level. And yes, our main loop also modifies the decision. So it's not like the decision level is strictly increasing. It increases until a conflict happens. Somehow that analysis of the conflict then tells us how to jump back. So it's not recursive function calls, but there's this sort of deeper decision levels happening, and then the analyzer tells us where to jump back to and go forward from there. But presumably the new clauses we add will lead to the variable picker behaving differently, so that we don't get stuck in a loop of like, okay, we backtracked and we picked the same variable over and over again. Somehow these new clauses that we're learning and adding are going to guide the variable picker in new directions. So that's the piece we haven't learned about yet. This is the heart, but we need to learn how these valves work now. How the as it's pumping, what are these internal smaller machines that it is based on doing? So let's learn about the variable picker. I might need a 5-minute break from talking and thinking before I continue. So if anyone's in chat and wants to throw stuff out, you know what we'll do? Something a little lighter. I have on this, while I'm waiting to see if anyone wants to chat, now's a good time. I'm going to do something just go and check out this recommendation that I got from chat earlier. Oh, let's see. What do we have here? Okay, very popular. Like to see that. That means it's probably good stuff. Largely in C++. How big is there any way to tell on GitHub, like, how many lines of code the thing you're looking at is, or like how many megabytes of data is in the repository? I'd love to get an idea of how big this is. It looks like, you know, it's got like Docker. It's got this, like, it could be a fairly complicated package, which I would need to take time to get into. But let's see. Z3 is a theorem prover from Microsoft Research. Pre-built binaries for stable and nightly release are available from here. Z3 can be built using Visual Studio, a makefile, or using CMake. It provides bindings for several programming languages. So the fact that it can be built with Visual Studio gets us closer to a situation where I can, like, with makefile and CMake, I have to unravel those by reading scripts, whereas with Visual Studio, I can unravel it by opening up the Visual Studio project, at least, because I am familiar with Visual Studio enough to maybe see what the build targets look like there and what the options are. And that also makes it very likely that it's easy to just use CL and get it up and running, right? If Visual Studio can build it, then that means I can write a bash script much more easily, much more likely to work on a bash script. I got a note here from someone named Babel. Z3 is a bigger SMT solver than, say, Minisat. So yeah, I have Minisat. The problem is I wasn't able to build Minisat yet. Maybe I could put more work into trying to build Minisat. So I have two different goals. One of it is to read this stuff and learn how it works, and the other one is to get something building and working so that I can step through it. And Z3 was recommended as something that does, in fact, build on Windows. And I'm seeing, because it says Visual Studio here, that that is definitely true. Whereas with Minisat, at least the, like, 15 minutes I spent hacking around with it last night looked like it might be more difficult. But it's an interesting recommendation. It does look like it's so much more complicated than the other ones I've looked at so far. Let's look at, yeah, so here's our source folder. Here's where they implemented it. Yeah, so our API folder, definitely this is a big, intimidating, and they're doing a lot of work here to, like, port a bunch of languages. Wow, yeah. So I'm going to say Z3 is probably not where I want to go next, because even if the only thing that Z3 might be for me is it might be the one that I can actually figure out how to build and not have to go farther. But this is very far from, like, my dream, which is to find something equivalent to a single header C library for this. So I don't think that I'll spend more time here. But yeah, Minisat I have in the list already. So if I have someone in chat recommending it, then maybe you can also help guide me to, like, how to understand how to build this a little better. Why did I run into problems building it before? Right, it had a dependency on zlib, and I just bounced off of that. I forgot about that. Maybe I could go try to figure out how to set up zlib for it to be happy. Yeah, the only issue I'm having is it looks like it assumes a Unix system where you can just sort of pull in the dependencies with a dependency manager like apt or something. Does it have a C# version? maybe I just downloaded the wrong package for my purposes too. Like Minisat's a little confusing because I couldn't find anything, but they're like, here, let's pull up. When I go to Minisat, here's what I see. And I look around here, and honestly, Oh, I don't think I saw this before. I don't know how I missed a GitHub link. Minisat. Yeah, this is what I have. I think I downloaded like a tar GZ thing before, so this is a different path, but it looks like a very similar. Looks like a very similar situation. Yeah, maybe we'll try to play with Minisat and we can try to get past the zlib dependency. Maybe that's what I'll do next. So we took a look at, let's see, where's my, all right, we did take a look at this. Minisat need to resolve a zlib dependency to make progress on building. But maybe that will be fun. Maybe we can try to get Minisat to build and look through that. And I think Minisat is, like, the one I'm looking at now is just a, it's just a really small one. It doesn't have the converter to conjunctive normal form. I bet just Minisat is going to have all that good stuff. Right? Like, if you look at Minisat's website, it's got this, like, it's won all these awards at different SAT competitions and stuff, so it feels like it's probably going to have a lot of those features built out that are missing from C. Now, it's Minisat. If we take a look, Minisat is a C++ project primarily. So Alex, since links won't get through on the Twitch chat, but you can send it to me on a whisper, and I can take a look. Yeah, okay. I got the impression looking around last night that Minisat was the one I wanted to make progress on. I just didn't feel up to like resolve an external dependency on zlib myself. But yeah, let's make that our next step. We'll look at that. This CDCL solver that I'm looking at is kind of helpful for giving me some bearings on what this space might look like. But I think Minisat's probably more in the strike zone of what I really want to be learning. All right, I think that has been a nice break. If you, again, comments in chat is always welcome. I'm going to keep doing this, but you can keep it coming if you want. So it looks like the variable picker is going to be a little bit more interesting. It has a bunch of references to appearance map. Where's let's bring back the side-by-side mode. Yeah, so there's just going to be a bunch of these little functions in this file. I'm going to go into unbalanced side-by-side mode. So this will be my navigation panel, and this will be my main panel. Yeah. Well, I think this was the right place to start. I made a lucky pick, just on the sense that like it was such a small amount of code that this might be the right place to learn. And I'm always taking a risk when I'm learning that I'm also learning someone's bugs. Like I don't know that this is, but like the general structure, the general vibe of the space just starts to get more clear the more different approaches you look at. And sometimes people have a clever idea of how to structure something. And so I'm just like sometimes if I'm going to get into a topic, read some people's code on it and see what they do at different points and use your taste to pick some of the best parts, right? Kind of what I'm going for here. Ah, you were gonna do a PhD on sat solvers. That's cool. I don't think I was ever that interested in sat. I've become interested in sat as something I would like to play with. Like I would like to really spend time on the usage side of a sat solver. I'm not that interested in the implementation details, and I haven't gotten into it before. It is kind of a cool topic. Like I like researchy stuff where it's like most of the stuff I've done that's what am I trying to say? There is a part of computer science where you just work on organizing and structuring stuff that's like operating systems and text editors and so on. And then there's the like, hey, here's a real tough problem, and what can we do about this? And so in that space, where I spent my attention was like geometry stuff, all the stuff related to game dev. So like, especially how do you do like interpolations and linear algebra stuff, that kind of thing. But I kind of am in the mood to just learn a lot of other stuff like sat solvers. AI is interesting, but it's kind of hard to do as an indie person without resources to like get to access to the right tooling to get started. But there's like stuff like this where you could just look at implementation and look at like how are we doing this, and that's interesting. But I'm also sat solvers are interesting because once you can conveniently start using one, I feel like there are ways to incorporate it into programming and creativity that would be a lot of fun to play with. Like I have some ideas I want to play with. All right, I want to read this. So pick a variable. How do we pick a variable? We got a formula. We got a model. We want to output a variable index and the value for it. And this is a guess, not a sure thing. So we're kind of just heuristics here. We build something called an appearance map. All right, we need to know what that means. Okay, so these are there not. Let's turn off line wrapping on the mini one. I'm gonna just do some rearranging here. Again, I just like to have my summary on the left-hand side, and so there we go. That kind of, I think, roughly reconstructs the spirit of this file, but in a style that makes sense to me. So an appearance map has an integer buffer, an integer indexes map, and a count. Let's look at what happens when we create one of those to get more information. So, the appearance map hidden pointer. Got to watch out for that. Okay, so we create the appearance map memory. We say for the number of unassigned. So the number of unassigned is going to go into. No, it's not even going into count. So number of unassigned gets lost when we construct a map, but presumably the caller is going to know about it. Like the algorithm is set up so that you don't need to know that count. We allocate 2 integers for each unassigned, whatever that's going to mean, and put that in the buffer. And we clear it to 0. Okay. Then we allocate one integer for the index map for each unassigned. And we have a count of 0. So that's how we create our map. Presumably, yeah, we have to be able to free it malloc and free style. Okay, so what happens next? We have this map of zeros. Maybe I should go and read about the appearance map. It feels like this is going to be all implemented in terms of appearance map operations. So what is an appearance map about? We can register something. So we take in a map and a variable, and when we do that, okay, so this just lets us put variables into that indexes map. Okay. So we are registering a variable with the system. We get an index by saying, here's the variable I want, and it scans. Oh, this is a binary search. So presumably the variables must be coming in increasing order so that we can put in a variable and look up its index. Okay. And in this particular case, we want to say either you find the match or you return that you didn't find a match at all. Sometimes when you're doing a binary search, you're looking for the closest, like, similar thing, and sometimes you're like, no, you find it or you don't tell me you found it. So this is the second case. If there's no match at all, you get a -1. If there is a match, you get a valid index inside the range of registered variables. Okay, record, and that was, so these are not in order. That's get index. Record literal. What does that do? We're going to take the literal, it could be positive or negative on this API, and make a variable out of it. So literal, I think the nomenclature they're using, literal can mean variable together with the either positive or negative version of that variable. And a variable is just always a variable. So like the variable x3 is the variable x3, then there's the positive and negative versions of x3 are each literals. That's what I'm picking up from the patterns here. Binary search for variable. So we grab the variable, we go get the index in the map. If the variable doesn't show up in the map, we just come out. We're just like done. But if it is there, we grab the record index. So this is where we go into that buffer. So there's two of the variables inside this buffer, two integers inside this buffer for each variable. And so there must be, the first one corresponds to the positive literal, and the second one corresponds to the negative literal. And then we increment it. So its appearance map tells us how many times a particular literal appears as we are looking at certain things. Got it. So this is a counter, right? This is saying increment the counter for this literal. And then that literal goes into this binary search with the variable. So if it is the negative version of the literal, we drop the negation, find the index, use that index to find a pair, which is the count of positive and negative appearances of this variable. And then we use the original literal to figure out which one of those we're incrementing. Got it. What is get best assignment doing? So a map comes in. We're going to probably be sending out a variable and a value. And so this must be where we're actually going to, like, this is where the heuristic is showing up. So max variable index equals 0, max count takes in okay, so we're going to be scanning over all of the variables. So we have this count, right? For each thing in this count, remember this, let's look at the structure here. I'm just going to put some annotations over here. Buffer is an integer of num unassigned times 2, and indexes map is an array of integers of size num unassigned. I missed the 2. Num unassigned, and count is an integer in the range of 0 and num unassigned, right? Well, I appreciate having someone there to confirm that what I'm learning from, this is just example code from some person. I don't know, like, I don't know how seriously to take it. So I'm following their nomenclature and hoping that what I learned will export. So having someone in chat to verify that literal and variable do mean what I just suggested, like throughout the the space is good to know. Much appreciated input. Okay, so that's the structure here. And so as we're looping over this count, we're looking at each of these pairs, and it looks like we're just saying add those up. So take each pair, take the sum of them. Whichever pair has the largest sum wins the max count competition. And so at the end, we take the max variable index and the max count. Well, I guess we don't. Max count's just for the purposes of taking the max, right? The max variable index goes in here, tells us what variable, not what literal, but what variable had the most appearances. And then we look and see, is it more true or more false? I see. So what this is doing is saying like, hey, we're looking for a variable which has a lot of influence over the entire formula. Right, so we have this huge formula, a bunch of clauses ANDed together, and we need all of them to be true. And in there, various variables can appear, and we're saying, give me a variable that appears more than any other variable, so that it has the most influence, and give me the assignment that is more popular for that variable. So that'll be my guess that I add to the formula, right? Or rather, that's the guess that I'll use to assign a variable and make progress. Interesting. So that's the heuristic. Makes perfect sense. And I assume that this is just, like, now that I've seen, it's funny, once you've seen the pieces, I haven't even read how they're put together, but I assume that's what's going to happen. We're going to loop over all of the clauses. We're going to take each clause and loop over all of its literals. Oh wait, there's hidden logic right here. If, so this is the same as saying this. So if this clause is unassigned, so we're doing what I explained. We are looking at all of the clauses and looking at the most popular variable, but we are disqualifying clauses that have already been resolved. So if we're looking at your clause and you already evaluate the true, then we are not interested in the contribution that your clause makes to the question. Interestingly, there must be something I'm missing, because this could still generate guesses to create assignments that have already been assigned. Like, this has to somehow disqualify variables that have already been assigned, right? It's looking at each literal, and it's recording each literal that it sees. So inside of a clause, even if the clause is unassigned, right? The clause doesn't have a determined outcome yet. It is not the case that at least one of its variables is true. It's still possible that some of them are false, right? Like, it's still possible that some of the variables are fixed. And if some of the variables are fixed, I'm just a little, because the map, where does the model get used in this code? Unfortunately, the model has the name M, so as I search for cases of the letter M, I find a lot of false matches. Yeah, what is this part? What is this part that I'm not looking at? Number of variables. Right. Okay, so what this is saying, again, let me rearrange logic. For each unassigned variable, we register it. Now remember, num assigned. So here's how we calculate the number of unassigned variables. We have the total number of variables in the model, and remember the model is tracking how many variables are assigned. So this is giving us the number of variables that aren't assigned, and then we loop through all of the variables once, and any of the ones that are unassigned, we register them. That registration is sort of saying, I give permission for this particular variable to go into the system and be tracked. Then if I record a literal, remember this? Okay, it's a little bit subtle. I'm not sure I would do it this way myself, but I understand I understand the structure that this is built with. And maybe it is more efficient this way. I kind of feel like it'd be easier to do it a different way. But you give it a literal. It then goes, okay, let me binary search, see if that literal's available in the map. If not, nothing happens. So remember, the only ones that are registered with the map to begin with are the unassigned ones. So in fact, it is making sure that only unassigned variables are being played with. Okay. So yes, we look at all of the unassigned variables, we look at all of the unassigned clauses, and we run a little competition to see which unassigned variable has the most influence over all of the remaining unassigned clauses, and we assign it its most popular outcome, right? If it would rather be true or false. Now, if those are very close to each other, the heuristic is interesting, right? This gets interesting. If it's the most popular variable, it might be that its true and false appearances are very similar in their numbers still, and so it might not be obvious that one or the other is more likely to make the rest of the formula true, but it's still the right variable to fix in the sense that it has so much influence that figuring out if it should be true or false should happen earlier in the decision path rather than later, right? It's so wide-reaching that it's more likely to lead to other variables getting forced into a certain path or something like that. So I think that is the idea behind the heuristic. More important to pick the most popular variable, and secondarily interested in picking the assignment for that variable that is more likely to be useful. But that second point is less important than picking the more influential variable overall. That's the interpretation I'm giving to this heuristic. Okay. And then it figures out the best assignment. We already figured out how that part works, and that sets that. Okay, so we now know how the pick variable part works. Done. Back here, the other thing we wanted to look at was the analyze conflict function, and I'm going to pull that up, but once again, I need a breather. So I'll just hang out for a sec. Maybe while we're taking this breather, we can look at this zlib issue. Someone in the chat earlier mentioned that they successfully built zlib on Windows. Are you still here, Bitwitch? So should I be grabbing like this copy of zlib off of GitHub? Or did you get the zlib source from another place? Yeah, this looks like it might be pretty easy to build. If what they're saying in chat is true, then it's just a matter of like build all these C files and link them together into your project or into a static file or something. I don't see. Let's try zlib source. See if that links us to. Yeah, here we go. All right. That's probably a good place to start. Grab the zlib source. We'll make more progress on that soon. Let's see, how complicated is the conflict analyzer? 80 lines of code. Okay. We're almost done with CDCL solver. This has been super helpful for me as a first step into learning this, so I want to wrap it up. And again, big thanks to these folks who created this. It's the best intro code to the topic that I found while I was looking around. So. Okay. And it's just one big function. There's no like data structures or helper functions to learn about this time. So what are we dealing with here? In terms of the signature, man, it's a big list. It's a big list of stuff. Formula M, decision level. Yeah, we figured this out earlier, right? We don't know how it works, but we talked about it when we looked at, I summarized this over here in the solver. Formula model, decision level, clause index. The clause index that goes in comes from this propagate function. So it's the clause that is in conflict, where it's the clause where all of the literals evaluate to false, and so the clause evaluates to false. And this is the decision level. I don't know what role that will play yet, but that tells us what decision level we're at currently when it goes in, and what comes out is what decision level we should jump to. I don't know how it's going to make that decision, but let's find out. So we look at the buffer of literals from the formula, and how many clauses we have. If the clause index is greater than 0, clause index. Okay, so we are bumping. Okay, we're trying to pull out. Looks like it's pulling out the clause of the conflict, and I don't know why it's doing it this way instead of, like, it has a helper for this, but maybe it just decided not to do that this time. Doesn't matter too much. It looks like it's. But yeah, it looks like it's finding the beginning of the literals for this clause that has the conflict and the count for that particular clause. Yep. This is the neat part, you say. I'm excited then. Did modify clause equals 1, while we did modify clause equals 0. Okay. Literal index equals 0. So we're iterating the literals of the conflict clause. Literal equals clause literals literal index. By the way, what does CDCL stand for? I should look that up. Conflict-driven clause learning. Conflict-driven clause learning is an algorithm for solving the Boolean satisfiability problem. Okay, so CDCL is the name of the algorithm that is implementing this solver. And this is the conflict-driven clause learning algorithm. Okay, that's the part we're learning now. We're learning about how it uses a conflict to learn a new clause. Okay, literal index is less than clause count. We look at each literal. Literal equals clause literals, literal index. Okay, right, so literal index is the index into the clause. We're iterating over the clause. This is the actual literal value, this is the integer that represents what literal we found there inside the clause. We then grab the assignment for the variable. So this is the variable that it corresponds to the literal. The -1 makes it the index for that variable. Because remember, our variable can't use the value 0 to represent itself because it wouldn't have a corresponding negative. Right? So this has to be 1 based so that 1 and -1 are the smallest pair of literals available. My stream is dead. Let's try to stop streaming. I'm just going to try to stop the stream on OBS and start it again. See if that does anything. Now OBS is still saying it's trying to stop the stream, but it's not succeeding. Also, maybe they did. No. What happened? Alright, I'm going to stop the recording just because maybe I need to restart OBS.